While leaving a shopping centre, a mathematician accidentally drops a bag of apples at the top of a ramp of length 10 metres and width 2 metres. The diagram below shows the top view of the ramp. 4 of the apples roll safely to the end of the ramp, while 6 roll off an edge and splatter on the ground below. The mathematician decides to create a simple model by assuming that the apples roll independently of one another along straight lines from the apple drop point, which we can see on the diagram here. Direction of each apple rolls, theta, is an angle measured about the apple drop point and is uniformly distributed over theta between 0 and pi. Apples that roll along the line with the sector marked by alpha will arrive safely at the end of the ramp, while others will roll off the edge. And the first thing we want to do is determine the value of alpha. So there's a couple of ways we could do this. One way is just to simply go straight down the middle here and make that right angled. And then this would be 1, and we can see from here that the length is 10. So in that right angled triangle, we have that the opposite over here is 1, and the adjacent there is 10. So we can use the tangent. So we have that tan, now remember this angle here would be half of alpha, so that would be alpha over 2. That is equal to 1 over 10. So alpha over 2 is going to be the inverse tangent of 1 over 10, and then alpha would be twice the inverse tangent of 1 over 10. Now we need to make sure here that we're in radians, and then we can just go to the trig tab, and we're going to do 2 times the inverse tan of 0.1, and that's going to give me 0.199. So correct to 3 decimal places. Hence show that the probability, P, of an apple rolling safely to the end of the ramp is P is equal to 0.063, rounded to 3 decimal places. Now we're told that the angle theta is distributed uniformly over 0 to pi. Therefore, our probability is just going to be alpha over pi. It's this angle out of the angles from 0 to pi. And we have our value of alpha, so we can just put that in there as the last answer, divide that by pi, and execute, and you can see 0.063 to 3 decimal places. As required. Now, moving on to part B, determine the probability that of the 10 apples, 4 or more make it safely to the end of the ramp. Well, if x is the number of apples that make it safely to the end of the ramp, that's going to be binomially distributed with 10 trials and a probability of success of 0.063. And we want 4 or more, so the probability of x being more than or equal to 4. And we can do this on the calculator. I know you've done this sort of thing loads of times, and I haven't always done this as we've been going through these videos, but let's do it this time. So binomial CDF, so we're going to go from 4 up to 10 with 10 trials, 10 apples dropped, and 0.063, and that gives me 0.0024. The mathematician decides to purchase another 20 bags of apples, i.e. 200 apples, return to the top of the ramp, and break each bag open one at a time. After the experiment, a total of 63 apples have rolled safely to the end of the ramp. Using this sample of 200 apples, calculate a 99% confidence interval for the population proportion of apples that will roll safely to the end of the ramp. Well, we know that our p hat here is going to be 63 out of 200. That's the 63 that went to the end of the ramp out of the 200 apples. And that is 0.315. Now, you can certainly do your 99% confidence interval by calculating 0.315, take away 2.576 times the square root of 0.315, 1 take away 0.315, divided by 200, and then the other end of it will be the same thing, but just with a plus there. This is the Z99 value. But in all likelihood, you're going to use an E activity for that. So we'll just go to the E activities, and I'm in applications at the moment, so I'm just going to get my methods open. Yes, I am sure. And we are going to go confidence interval for proportion, and we're going to zip up to the top there, and we are saying that there were 63 apples out of the 200. So change that to 200, and we wanted a 99% confidence interval. We'll execute on that, and it's going to give us that. I probably want that as a decimal, so let's just go back and run that again from the top. So it will be 0.2304 and 0.3996. Okay, so what does the confidence interval from part C suggest about the validity of the model assumptions used to calculate the probability in part A2? Well, our answer from part A2 was 0.199, which is not in the confidence interval. So, and you need to write something like this down, the proportion calculated in A is not within the confidence interval, and that suggests that the model assumptions may not be valid.